Alright, welcome back to the number theory slides. Let's learn some more cool stuff about numbers. So the next place I want to go, still on the topic of primes, let's talk about primes as well as modular arithmetic, because there's plenty more to say there. So here's a cool theorem. I won't prove it to you. I'll prove it to you with my hands up in a hand-wavy way, in a way that's not exactly convincing, but hopefully it's a good enough example for you to remember it by. So here is the theorem. If p is a prime number and a is an integer and a is not divisible by p, so there's a lot of like side conditions. If all that stuff is true, then here's a cool fact. That number a to the power of p minus 1 is equal to 1 when you're working in mod p land. You're always doing mod p by this, where p is a prime number. Okay, so that's kind of cool. So here is the hand-wavy proof of that. So the idea is going to be that multiples of a are going to cycle through every non-zero element of ZP. And what is ZP? Whatever it is, where p is a prime number, it's going to be all the numbers in this set. All the numbers from 0 to p minus 1, right? Because those are all the things that you get by doing the remainder by p. So 0, 1, 2, 3, all the way to p minus 1. Those are the numbers in ZP. That's all you can get. So let me show it to you. This is trying to say, let me show it to you for p equals 5 and a equals 2. So let's say we got, we're doing 2 to the power of 4 mod 5, or that's p. So let's work our way up there. Here's my proof to you. Multiples of a cycle through every element of ZP. Watch. We got every non-zero element, by the way. So once 0 kind of keeps things 0, as it does in normal arithmetic. But like 2 to the 0 mod 5, well, that's just 1 mod 5, which is 1. 2 to the 1 mod 5 is equal to something 2 squared. We'll get there. So 2 to the 1 mod 5, that's equal to 2 mod 5, which is still 2. And then 2 squared, that's congruent to 4 mod 5. Remember that notation. 2 cubed, that's 8, but it's congruent to, if you do mod 5, that's 3. Yeah. And then 2 to the 4, that's 16. That's congruent to just 1, like I was trying to say. So look at how this is happening. So this is 2 to the 4. P minus 1 is 4. It's working out. So that checks out. But look at how it's cycling through all the numbers. 1, 2, 4. It doesn't have to be in order. 1, 2, 4, 3. And then it's back at 1 again. Okay? So, yeah, that's my hand-wavy proof. This will work for any a and p, assuming a isn't divisible by p. It's a cool little idea. It's invented by a dude named Fermat, or Fermat, I guess. It's his little theorem. He had a much bigger theorem, I guess. So, yeah, my proof is my hand-wavy proof. This is not correct, that you can't, like, assume this is ever true, but you can take my word for it. The idea is that the only way for this cycle to go back, right, to restart and go through all the numbers again, is to get back to 1, right? Because then you'll multiply one more time and get your original 2, right? 2 to the 1, that's your 2. Because, obviously, a to the p, you do that p times, you can see how that's going to be equivalent to a mod p. It's kind of like it cycles that many times. Every p, everything you're taking a modulus by, it's going to cycle, and you'll be back at the start. And so 1 before that would have been the number 1. Okay, that's the idea. So if this is true, obviously this is true. You multiply by a one more time. I hope you see that. So that's kind of the idea. That's Fermat's little theorem, Fermat, however you want to say it. We'll have to look him up on Wikipedia. So okay, let's talk about another theorem. This is the GCD theorem. So we learned a little bit about GCD. It's kind of hard to compute just on paper, because you got to write out the prime factors. It's hard to find the factors of something, right? So let's see if there's an easier way, and there happens to be an easier way. Right, so here's the GCD theorem. Let x and y be two positive integers that you want to take the GCD of. Then the GCD of x and y is equal to the GCD of y mod x and x. Interesting. So we'll prove that this is true. And this happens to be the GCD on two smaller numbers. So this is like getting closer and closer to smaller things, which is interesting. That's probably easier to find answers for. So this is what we're going to prove, and what do we need to show, right? The way we're going to prove it, the way that this checks out is that we have to prove that, all right, the GCD of x and y, like these are divisors we're talking about. The greatest common divisor of these two things is the greatest common divisor of these two things. And so we have to prove things about stuff that goes into stuff. We'll prove that every divisor of x and y, we're trying to consider their divisors, all those divisors will also be divisors of y mod x, right? Every factor of x or y is still a factor of y mod x. So we'll show that, okay? And then once we've shown this, right, that's like the first bit. But if you know that every factor they have in common, then you can go and find their biggest one, because they're obviously going to share the biggest one as well. Okay, so that's why it'll be true. So if we prove both of these things successfully, we'll have proven the original theorem. So let's prove that. Okay, so here's kind of what we're going to show. All right, here's spelling it out in math form. So for all f's, x's, and y's, these are integers, if f mod x and f mod y, you have both of those, if and only if, right? You know that f divides x and f divides y. F is a factor of x and f is a factor of y, if and only if f is also a factor of y mod x and also x. Why not, right? Because this is like GCD stuff on the left, and f is a factor, right? And just the GCD stuff on the right. So we got y and x, right? So if f is a factor of x and y, if that is true if and only if f is a factor of y mod x and x at the same time. See that? So this is an if and only if. It says we haven't proven one of these yet. This is like side A. Got all this stuff on side A, got all this stuff on side B. And essentially, to show an if and only if, you got to prove both. You got to prove this way, A implies B, and you got to prove the other way, B implies A. See that? So you need both of those. And of course, this is equivalent to B implies A in that direction. And so let's prove that, okay? This is the theorem we're going to show, both of these directions, all right? Both of these directions. So this is the only if direction, and we'll make it work, because the goal is to come up with an algorithm. Like this will lead to an algorithm because this is a smaller number, and then eventually it'll stop, and it'll have an answer, okay? So that's pretty cool. So yeah, let's prove both of these directions. I'll show them to you. They're going to be just normal direct proofs. Like if we go in this direction, it's going to be like assume this, right? Assume this, prove that. If we're going to go from left to right, you're going to do the A implies B first. We got to do both of them separately. It's like two cases to the proof. So in this direction, we have this. It's a direct proof. This implies this. So we'll assume the A part, prove the B part. Okay. So assume f divides x and y, and then we'll prove that f divides y mod x, and then also x still. This one will be easy. Okay, let's do it. So assume f divides x and f divides y. Okay, what do we get? So, we need to show both of these. We need to show this is true and this is true. This is easy, right? Because we're assuming it. It's easy to show f divides x if we're assuming that f divides x. So by assumption, right? By assumption, we know f divides x. All right, that's cool. Now we need to do other stuff. Well, let's try to get this one. That's the harder one, of course. So, all right, what is y mod x? Y mod x, by a previous lemma, right, from way back here, y mod x is equal to y plus kx for some integer k. You see that? See how I'm translating those variables? So that's actually going to help us here. Y mod x is equal to this, y plus kx for some k. Don't know what, doesn't matter, but this is true about it, okay? And then, all right, y plus kx, this is going to be a really cool combination of other theorems that we've had. So that one plus another one, y plus kx, y mod x, which we know now is equal to y plus kx. That's the same as like 1 times y, right? 1 times y plus k times x. What does that look like? Have we seen that before? That's a linear combination. Remember that definition? That is a linear combination of x and y. Where is that idea? I think it might be up here. Linear combination of two numbers. Looks like that. Okay. Where am I going with this? We have a theorem about that, don't we? It is a linear combination of x and y Therefore, by this theorem, right? By this theorem that we proved, coming back for us now, if I know that x divides something and x divides something else, x divides any linear combination of those two numbers. So just applying this idea, because we know that now y mod x is a linear combination of x and y, and I know that f divides both of those, f will divide this linear combination, which is y mod x. You see that? So by that theorem, therefore, that second theorem to the rescue, f must divide y mod x. Isn't that lovely? That's pretty cool. So that's the first step. That's the left to right direction. Let's do the right to left direction. This is the if side, the if part. So we're gonna do from here to here. This side implies this side, so we're gonna assume the right, use that to prove the left. All right, and after that we'll have proved the entire if and only if. So we'll assume this, prove that. Well, let's make it happen. So assume f divides y mod x. Got to spell it out. And f divides x. We got to show both of these. Well, we can show this one very easily again, because again, by assumption, we're assuming f divides x, so obviously f divides x still if we're assuming it. By assumption, f divides x. And then, all right, let's break down y mod x again. Y mod x, we know what that means. Y mod x is equal to y plus kx for some k. And now, I'd like to know that f divides y, so I need to know that y is equal to some multiple of f, right? I have an equation involving y here, so let's solve this for y. That might help me here. Solve for y. So, what do we get? Y is equal to, well, it's y mod x minus kx. So, which is 1 times, right? 1 times, well, let me just write it out. It's equal to y mod x plus kx, and this is the same as 1 times y mod x. And what do you know? So that means y is a linear combination of y mod x and x. I know things about linear combinations, right? It is a linear combination of y mod x and x. Therefore, if I know, then I know that because I have this and this, if f divides any of those, either of those, f divides their linear combination, any linear combination of them, and y happens to be a linear combination of them, so f divides y. Yay. By that theorem, right? By that theorem that we proved last time. See how they're all just like building up on top of each other? That's so cool. So that gave us this idea, all right? That's proving some important facts for us here. Therefore, f divides y. Cool. And so that means the GCD of x and y, it really is equal to this. So they have the same divisors, so obviously they have the same greatest one too. So that completes the proof. That's lovely. And that leads to an algorithm, okay? If we just, because we know that these are equivalent, right? We've proven that this is equal to this. If we just keep replacing, right? If we just keep replacing this side with this side, those numbers keep getting smaller. Eventually, you're going to end up trying to find the GCD of 0 in some number, okay? And every number divides 0, so every number is a divisor of 0, excuse me. There we go. So every number is a divisor of 0. So, like, the greatest divisor is just whatever z was, okay? That's going to be the idea, okay? That's the proof. So eventually, like you're gonna do a bunch of work. You're gonna keep replacing this to this to this equals ... Eventually, you're gonna get down to this one, and then your final answer is just z. All right, that's how you do it. Okay, that happens to be the GCD of the original two numbers. And so let me prove to you that every number divides 0, right? So like 1 is a factor of 0 because like 1 times 0 is 0. 2 is a factor of 0. So this side, 0 is not very helpful, right? So what's the greatest common divisor of 0 and z? Well, it's going to be just z, okay? That's how that's going to work. The greatest one, because every number divides 0. But we're looking for the greatest one that divides them both, and so just z itself. Z is the bottleneck there, okay? So that's going on, and that gives us an algorithm, actually, to find the GCD of two numbers. It's called the Euclidean algorithm, or Euclid's algorithm. It was invented. It's actually claimed to be the first algorithm ever invented of all time. And so this was back in the BC era, and way before computers. This was the first algorithm to compute the greatest common divisor of two numbers. And notice that it has nothing to do with finding prime factors. Much, much easier. It converges very quickly. It's really, really cool. All right, so let me give you an example of that. Let's compute the GCD of 80 and 61. All right. So I like to compute the GCD of 80 and 61. I don't know what the answer is, but this is my x, this is my y, and I can keep replacing this with the GCD of y mod x and x. All right, so let's see. What is y mod x? 61 mod 80. Well, actually, it goes in 0 times with 61 left over, and then we'd put x next. So it's 80. So that's kind of funny in that we had y was equal to 61, x is equal to 80, and we calculated y mod x, right? We replaced it with GCD of y mod x and x. Y mod x was 61. So you might think it's doing nothing because it just flipped the numbers, but now it actually is going to do something, okay? You need the first number to be smaller, and it'll switch them if they're not like that already. So this, all right, what's this now? This is x. This is a new x. This is a new y. We have, okay, that's the GCD of y mod x this time now, 80 mod 61. All right, 80 mod 61 goes in 1 time with 19 left over, yeah. So that becomes the GCD of 19, and then whatever the x switch, which is 61. See how I'm replacing stuff? And so that is now x and y, and we'll replace that with the GCD of y mod x and x all over again. So that's equal to the GCD of y mod x, 61 mod 19. No clue what that answer is, but let's get out of that for a second. 61 mod 19. That's 4. Okay, the 4, and then the original x, which was 19. That's equal to the GCD of y mod x, so 19 mod 4. 16, 17, I think that's 3, right? 3 left over, and 4. GCD of 3 and 4, which is equal to the GCD of y mod x and x. This is a y, this is x, right? 4 mod 3, that's 1, and the original 3, right? And then GCD, that's equal to the GCD of y mod x. 3 mod 1 goes in 3 times with 0 left over. And then the original x was 1. So actually, and then GCD of 0 and 1, the GCD of 0 and anything is the other thing. So finally, we got something that looks like this. The GCD of 0 and whatever was that whatever. It's equal to 1. So the final answer is 1. And so actually, these numbers are relatively prime. Their greatest common divisor is 1. Okay? Isn't that funny? That's pretty cool. So that's pretty nice. They are relatively prime numbers, and that's your algorithm. You just keep replacing this kind of stuff until you see that the first number, that x, was 0, and you can totally make an algorithm out of this, and everybody has. So let's go back to this. Here I have predefined the GCD algorithm. Obviously, I'm going to do it by recursion, and so I'll print out every time I call the GCD just to make it fun for us. But let's do the first one only. I'll comment out the other one. This is a GCD of 80 and 61. You're going to watch it work. And so base case is like if you're trying to take the GCD of 0 in something. So if x was 0, the answer is the other thing, the y. Otherwise, you're going to keep on replacing. You're going to compute the GCD of x and y is the same as the GCD of y mod x and x. See that? And so here it is finding the answer 1. And you see how it's calling them slowly but surely on and on and on in the exact way that we did it. It's converging. And so here's the GCD of 12 and 18. That was from the example above when I defined all this stuff to you. Where was all that? Was it this? Yeah. So to originally find that 6 was the answer, I had to make prime factors, but that's like really hard in general. With the GCD algorithm, you don't have to worry about that. You just keep on replacing 12, do 18 mod 12, that's 6, GCD of 6 and 12, GCD of 0 and 6, okay, the answer is 6. And so quickly, without even worrying about prime factors, it's found the answer, which is really cool. There's rapid convergence. It's just a neat little algorithm, okay? And so here, you try. Find the GCD of 42 and 30, and you'll use this algorithm using these ideas that we talked about here. Honestly, if you want to do it fast, you can just write y first, then x, and you'll keep on taking mods in that order. It'll always work out. So give that a try. So assume this is x, assume this is y, and then write y first and then x, right? Because that's y and then x. And then you have, like, so that was 30 and 42, and do you see how now you're ready to take y mod x? It's just right there for you. And then you can compute y mod x. That will become your new x, right? So what's y mod x? That is, well, okay, that's, oh darn, that's just 30. And then now you're going to shift everything over. Like, all this shifts over by 1. Dun, dun, dun. All this shifts over by 1. And now this becomes the new y. This becomes the new x. And you're going to take their mod and get the y mod x again. So just keep on making it smaller and smaller. And so that's how that works. Okay? So just keep on shifting it over. And so now this is the new y and x in that order. So now we're going to do 42 mod 30 to get 12. And then now this is the new y and x in that order. 12. You see how you're just keeping the other one along for the ride. So 24 with 6 left over. And then 12 mod 6, it goes in 2 times with 0 left over. And so the second you hit 0, that's like the end, that's your stopping condition. You get to 0. Just the one before 0, that was your y for that one, right? Because this is y, this is x, a GCD of 0 and 6. The answer is 6. And so that's how I like to write it out, instead of like doing all this. Like that's the easier way, okay? So that is how you find the GCD of two numbers like on paper and show your work. Here's an artist rendition of Euclid, by the way. Very famous mathematician / I think philosopher as well. And so that's the Euclidean algorithm, all right, or Euclid's algorithm. And you can do cooler things with it if you extend it, we say. Okay, so let's talk about that. So it turns out, just so happens, that you can express the GCD of two numbers as a linear combination, weirdly enough, as a linear combination of x and y. Why you would care, this will be important later, I promise. It's important to care, but this leads to an algorithm. Okay, so let me show that to you. So let's see here. So here's kind of it being spelled out logically. So let x and y be your integers that you're taking the GCD of. Then there are integers s and t such that whatever that GCD of the original x and y was, the answer is representable as a linear combination of those original two numbers x and y. All right, I promise this is useful. It's really good. It's useful for encryption. We'll get there, okay? But that's the idea, all right? So the Euclidean algorithm, we say, it can be extended. We can take this scratch work that we've been doing and use it to compute these two coefficients s and t such that we finally have a linear combination, all right? So you can extend the Euclidean algorithm into the extended Euclidean algorithm to make it happen, and you just like take this scratch work that you did to compute the normal GCD, and then you kind of work backwards from that scratch work, okay? So the way that this works out is that we're going to be using the division algorithm, all right? Remember, this is the division algorithm. You're dividing n by a d, and you get like the q and the r back. You can use that to solve for stuff. Here we're using like x and y, we're dividing by things. But what are we doing? We're doing what? Y mod x all the time, right? In our algorithm. But if we plug that into the division algorithm, where like n was the y, d was the x, because we're doing y mod x to get the r, right? Into the division algorithm it goes, you get that instead of n you have y, instead of q you have the division, right? Q is equal to y div x. sorry, this is q, but it's going to be y div x times the x, right? Because d is x, and then plus r, which is just, which is y mod x. Plus y mod x, that's supposed to be an x, plus y mod x. Okay, and then you can solve. You can solve for r, because that's what we're going to be computing when we compute the GCD, right? Plug in the y mod x. So what is y mod x? But, well, just solve for it. It's going to be y minus this bad boy. Y minus y div x times x. Okay, and this is going to be the magical formula that you're going to keep on reusing. Okay, this will make more sense with an example, I promise. But we're going to use that information, working back with our scratch work, to come up with that S and T value. Okay, so that's the idea. And like here is, let's see, how do I want to do this? Let me show you an example. All right, with 675 and 210. Okay, so you're going to write them out. Even if you do it backwards, right? You want to find like if this is your y, this is your x. You're going to write it out backwards. 210, 675, and they will flip each other. All right, so you get this. Let's compute quickly using this kind of style. Let's compute the normal GCD. So 210 mod 675, well, that's just 210. And then, okay, we're going to calculate. All right, now it's 675 mod 210. What's that? That's 45. And now this is your new y, this is your new x, and you'll take the mod. 210 mod 45, or sorry, just 40. No, it is 45, excuse me. What am I doing? So 210 now mod 45. That's equal to 30. Okay, and you need the scratch work for this. You can't just like plug it into the algorithm. 45 now mod 30. That's the new y, that's the new x. That's just 15, right? Let's confirm that. 15, and then we get 30 mod 15. That's 0, so we know that the answer, the GCD, was 15. Okay? And so the very last time we did this, right, now we're going to work backwards. We're going to work backwards this way with this idea. This was the first equation. All right? We know that we took 40 mod 35, we took 45 mod 30, and we got 15 back. This was our y, right? This is our x, and we took y mod x. All right? So according to our algorithm, our division algorithm, we can solve in this way. 15 was our answer for y mod x, right? 15 was equal to, I promise this is useful, is equal to the y minus, so 45 minus, let's see, 45 minus, let's see, what we got, y div x and x. So what was y divided by x? Dun, dun, dun. That was, it went in one time, so 1 times the x, which was 30. Okay, that's what's going on there. And like the normal division algorithm, even if you want to do it that way, you can always solve for it. You had that, okay, y was equal to 45 was equal to the quotient times 30, something times 30 plus the remainder, which was 15. All right, and the quotient was 1. All right, so that's how you discover that. And so you can use this idea to solve for the y mod x, which was 15. 15 is equal to 45 minus 30, something like that. Minus 1 times 30, and I think I want to use blue for this, actually, sorry. So 15 is equal to 45 minus 1 times 30. And now you're going to work backwards. All right, now you're going to take this stuff. Do you see now you have a new equation to work with? Of course that's not happy with me. Weird. Can I delete just that arrow? Let's see if I use this. I just want to draw back in the arrow for you. Slowly but surely, PowerPoint hates me. There we go. All right. I want to go back to the mouse for that and back to the pen for this. So, okay. Now I have that... I have an equation over here, and I've solved for 15 in terms of 45 and 30, but I know I have another equation in terms of 45 and 30. I have this one, right? Because this used to be a y, this used to be an x. and this was my y mod x. You see that? So likewise, I have some information about 210 mod 45 becoming 30, right? Using this idea. Because the answer, again, was, okay, 30 is equal to, I can solve for the 30, right? 30 is equal to, well, it was 210 mod 45. How did we get that? Well, it was equal to the 210 minus whatever the division thing was times 45. Minus something times 45. It was just the integer division. So it was 210 integer divided by 45 is 4 times 45, okay? And this is the kind of stuff that you're building up. Okay, so you got that, you got that. So you have all these equations, and you can keep on building them. So let me underline these later. Why does the eraser not work for me? It's so weird. Let's try it with my normal mouse. Oh, okay. Makes no sense, but okay. All right. So I've got this equation now, and you're just going to keep on finding every equation. Now you also have an equation in terms of 675 and 210. So 675 again, right? Because you did the mod, 675 mod 210 equals 45. Write this equation out for it, all right? 675 is equal to something, excuse me, 45 is equal to 675 minus, I think it's like a couple, maybe 3. 675 integer divided by 210. It went in 3 times. 3 times 210 with the 45 left over. Okay? So that's the answer. And you just keep on following all these equations because you're like, you got that mod that equals that mod that equals that. And all of these equations eventually will lead you to the GCD with 15. Okay? Watch this. Because we can start plugging things in. We have, all right, 15 is, I know something about 15. It's in terms of 45 and 30. It's a linear combination of 45 and 30. But I also know how to compute 30, right? How to compute 30 in terms of 210 and 45. You see that? 30 in terms of 210 and 45. And then I just keep replacing stuff, right? I can place the 30 with whatever this was, and now it's in terms of 45 and 210. And I can also replace the 45, right? I know what 45 is. It's in terms of 675 and 210. And once I do that replacement, now I have all of my numbers in terms of those original numbers, 675 and 210. You see that? And then I'll have an equation that gives me 15 out of that. Some combination of 675 and 210 giving me 15. Just got to plug all those equations into each other, all right? So let me take that, let me copy and paste it, and we'll spell it out. Okay, so let's copy this. Let's paste it here. This is the extended Euclidean algorithm. Just work backwards. You discover these equations, and then it works out. Okay, so here's this. We're going to use this as our scratch work, and now we can plug things in, right? Because I want 15 equal to some linear combination of 675 and 210. So, okay, I got 15. That's equal to 45 times 1 times 30. Okay. But what is 30? I have an equation for 30. Let's replace that. 30 is equal to all this, 210 times 4 times 45. So it's equal to, well, the original 45, sorry, it's 45 minus 1 times 30. And then 30 is equal, well, I still have the 45 minus 1 times, what was 30? Well, it's this, 210 minus 4 times 45. See, that's getting me closer to the original two numbers. 210 minus 4 times 45. Okay, there's that. And then let's bring all the 45s together and all the 210s together. So this is how many 45s? Well, it's 45 minus 210 minus, or sorry, plus now, plus 4 times 45. Okay, so that's how many 45s? That's 5 45s plus 210. 1 210. Oh, sorry, minus 210. Okay, so that's the same thing there. And now I know that 45 is also equal to this, right? 45 is equal to, so that's 5 times whatever 45 is equal to, 675 minus 3 times 210. And then I still have the minus 210. Okay, we're almost there. So this is equal to how many 675s? 5 675s minus, how many 210s? We got minus 15 210s here, minus another 210. Minus 15 210s minus another 210. So that's equal to 5 times 675 minus 16 times 210. Okay? And so this is, we finally have 15 being equal to some number times 675, some linear combination of 675 and 210. We found, do you see? Finally, we found our S's and our T's that equal the GCD. This is our S. This is our T. Or maybe I got them a little bit off, but that's the idea. Okay, let me use green for that even. There's my S. There's my T. Okay? That's what you got to do. So you do the normal GCD, you come up with all these things, you calculate using this idea now every equation that got you those things, that got you those remainders in terms of those original two numbers. It's like this mod this equals that produced this equation. This mod this equals 30, that produced this equation. So you write out all those equations, and then you plug them in for each other, starting with the last one, the one that actually gave you the GCD. Then you start plugging things in, eventually getting them in terms of the original two numbers, and then you have your answer. Okay? So that's how that works. And so that is, it's a lot of work, but it's very useful. Okay, so you try it now. Please represent the GCD of 42 and 30, so smaller numbers, it's easier, as a linear combination of those two numbers. Okay? So it's the GCD of 42 and 30, so this is like your initial x, this is your initial y. I like to write it out in the format that we had before, like first write the y, then write the x, so that you can do the normal mod, okay, kind of stuff. And so, all right, 30 mod 42, that's still 30. They're going to switch. You can always write the bigger one first for that reason. But all right, now we have 42 mod 30. That's equal to 12, I think. Yep. Now I have 30 mod 12. That's equal to 24 with 6 left over, so that's 6. And then 12 mod 6 is 0, so we're done. So 6 is the final answer. That's the GCD. And now I'm going to generate equations, right? Because I have an equation that gave me this, and an equation that gave me this. Technically, I also have an equation that gave me this, but it's useless, right? 30 mod 42, yeah, sure, that's 30. That doesn't really gain anything. These were the original two numbers. Just stop when you have an equation involving the original two numbers. So, okay. So this was like our y, the first equation. This was y and x, and this was y mod x. Now let's use this idea to express y mod x. Excuse me. So we got, all right, 6 is equal to, well, it's the y mod, that division, right? 30 mod something, or 30 minus something times 12. Well, what was it? It was 2 times 12, right? Because it's 24. That gave me 6. Cool, so that's my first equation. And then I'll do the same for this equation. 12 is equal to, so we got 42 mod 30 equals 12. It's equal to 42 minus, well, 1 times 30, right? It's just 1 times 30. And so these two equations, we went from this to these two equations, and now we're going to go working backwards, starting with this. 6 was the GCD. That's the first equation we use. 6 is equal to 30 minus 2 times 12. And we want a GCD of the original numbers, 42 and 30. So we have a 30 here. And then this is like a 12. That's useless. But I can replace this 12 using this equation. You see that? That's where we're going. So that's equal to that, which is equal to, replacing this 12 here, 30 minus 2 times, well, what is 12 but 42 minus 30. See that? And so let's simplify this. This is equal to 30 minus 2 times 42 plus 2 times 30. So how many 30s? We got 3 30s. And then how many 42s? We got negative 2 42s. So this is my original two numbers. And those are my coefficients. That is it. So now I have that 6 is equal to a linear combination of the original two numbers, 42 and 30, and that this is how. It's equal to 3 times 30 minus 2 times 42. That's equal to the GCD of those two numbers, and you can always find those coefficients. You can always generate this greatest common divisor. Okay? So that is the extended Euclidean algorithm. It is a little complicated. It takes some while to sink in. Hopefully those two examples are helping. But that lets us do some cool stuff, one of which is called calculating a multiplicative inverse. Okay, so this is modulus land again. We say that a multiplicative inverse mod n of some integer, call it x, is an integer that is in mod n land but not 0, can't be 0, such that, it's any one of those other numbers though, such that x times x mod n is equal to 1, okay? It's an inverse, it's a multiplicative inverse mod n, because when you multiply your x by that multiplicative inverse, you get 1, okay? When you're working mod n though. So remember what an inverse is. It's just like 4 inverse, that's 1/4, right? The reason 1/4 is the inverse of 4 is because if you multiply them together, you get 1. All right, that's what this is trying to say. You can find a multiplicative inverse of some number x working mod n. It's just the numbers such that when you multiply it and take the mod still, you get 1. All right, that's what it means to be an inverse. But it's going to be a weird looking number because we're working mod n, okay? And so one thing that the extended Euclidean algorithm is good for is to discover a multiplicative inverse, all right? It's only ever possible, it only ever exists when the GCD of those two numbers, of the number and then the thing you're doing the mod by, x and n, is equal to 1. So it only ever exists when this is true, all right? And if this is true, what can you find? You can find an s and t such that s times x plus t times n is equal to 1, right? Because that's what the extended Euclidean algorithm gives you if this is all true, right? And then, okay. And then you're going to take this equation, you have that now if you do the GCD algorithm and extended Euclidean algorithm. You have this if you're going to take all that mod n, right? Take all this mod n on everything. All this equation mod n gets rid of every multiple of n, right? They all go to 0. So then we have x equals 1 mod n. We have that equation. And then that means we've discovered the multiplicative inverse using the extended Euclidean algorithm. Just that coefficient gave us, that was the inverse, okay? So that must have been s mod n. If s is still too big, do mod n. Or if it's negative, you got to make it within the right range, right? That becomes your multiplicative inverse of x. Okay, so let's do this one. Let me show you an example. Let's find the multiplicative inverse of 7 mod 10, okay? So I'm going to take the GCD of 7 and 10. So I'll write the bigger number first because you know they're just going to flip after that. So 10 mod 7 is 3, 7 mod 3 is 1. Cool, 3 mod 1 is 0. So the GCD really is 1. It checks out. And now let me write my equations. Let's use the extended Euclidean algorithm. So let's write 1 in terms of 7 and 3. 1 is equal to 7 minus how many 3's? 2 times 3, right? And then let's write 3 in terms of 10 and 7. 3 is equal to 10 minus, well, it's just 1 times 7. 10 minus 7, okay? And so let's use this to calculate 1 equals something in terms of the original two numbers, 7 and 10. Because I want the inverse of 7 mod 10. That's why I did the extended Euclidean algorithm on them. Confirm that the GCD was 1, because now I have 1 equals 7 minus 2 times 3, but I can plug in something for 3, right? I can plug in those numbers for 3, so that's 7. So I keep on writing times instead of minus. 7 minus 2 times 3. Too much arithmetic for the day. So that's equal to, now I have 7 still, minus 2 times, but now I know 3 is equal to 10 minus 7. And those are numbers I care about. And so now let's get all these by themselves. So how many 7s? So 1 7, positive 2 7. So that's 3 7s total, 3 times 7, minus 2 times 10. Okay? So that's my equation. 1 is equal to 3 times 7 minus 2 times 10, which checks out. That is, that's pretty much the last piece of the puzzle. Now I know. My equation is this, right? 1 is equal to 3 times 7 minus 2 times 10, and I want the multiplicative inverse of 7 mod 10. So I'm going to take this equation and do mod n on it, and n was 10, right? So I'm going to do mod 10 on this. So this, any multiple of 10 goes to 0, and then I have this last equation left. 1 is equal to 3 times 7. And so that means 3 is my multiplicative inverse of 7 mod 10. Okay? which doesn't make a lot of sense. All right, I have to prove that to you still, right? So why is that true, right? Is that even correct? The multiplicative inverse of 7 mod 10 is equal to 3, and that's because, right, this checks out because 7 times 3 mod 10 is equal to 21, right? 21 mod 10, which is equal to 1. So really, yeah, 3 was the inverse of 7 if you're working mod 10. It's really weird. It's not like 1/7 or anything. It was another integer. Crazy. Okay, that's what gave us our answer. All right, I hope you see that. I hope that makes enough sense, because I want you to try now. Find the multiplicative inverse of 35 mod 48. Okay, so give that one a try, and use all these ideas together now. Give us a multiplicative inverse. Okay? Multiplicative inverse of 35 mod 48. So I'm going to do the GCD on both of these, and they better give me 1. Let's do the GCD of 35 and 48, so I'll write these out. What's 48 mod 35? Got 13 left over. What's 35 mod 13? 9 left over. 13 mod 9 is just what? 4 left over, right? Yeah, 4. And then 9 mod 4 goes in 8. Goes in twice to make 8 with 1 left over. So the GCD is 1. We're good there because 4 mod 1 is 0. We stopped before that. So I found the GCD, it is 1, and now let me generate my equation. So I got an equation with these guys, and then these guys. So many equations. And then I got 4 equations. Oh gosh, I'm sorry. Let's write them all out. All right, 1 is equal to what? 1 is equal to 9 minus, how many times 4? 2 times 4. All right, this one. 13 is equal, 4 is equal to what? Involving 13 and 9. Well, it's just equal to 13 minus 1 times 9, just minus 9. So that's good. And then what about this one? 9 is equal to what involving 35 and 13? 9 is equal to 35 minus how many times 13? I assume it's 2, right? 2 times 13 to make 26. So yeah, 35. 9 is left over. And then finally, I've got 13 involving 48 and 35. 13 is equal to 48 minus, so it's just minus 1 times 35, right? Yeah. So, okay. Now let's start with the first equation. Let's unpack it all. We'll get there eventually in the end. So, okay, I got 1 is equal to 9 minus 2 times 4. All right, let's replace using the next equation. 4 is equal to that. So I have 9 minus 2 times what was 4? 13 minus 9. Okay. So that's equal to 9. How many 9s? First of all, it's 1 9 and then positive 2 9s, so 3 9s total. 3 9s minus 2 13s. And then I can replace using this equation. What is 9 but all that? 3 times, okay, what was 9? It was 35 minus 2 times 13. And then still minus the other 2 times 13. Now let's try to simplify this. So how many, we got 3 35s, and then how many 13s? Don't know yet. We got, okay, so we have 6 13s from that one. Sorry, negative 6 13s from that one, and then another negative 2. So that's negative 8. So minus 8 13s. And then I know what 13 is. I can use this equation. So I still have my 3 times 35. Minus 8 times, what was 13? It was 48 minus 35. 48 minus 35. And so, all right, so that's how many 35s? I got 3 from this one, and then I have plus 8 from this one, so that's positive 11. 11 35s. Minus how many 48s? That's just minus 8 48s. Okay, so there we go. So that's my final equation, right? My final equation is 1 is equal to a linear combination of 35 and 48. So I want the inverse of 35 mod 48. So I'm going to take this equation, 1 is equal to all that. 11 times 35 minus 8 times 48. I'm going to do mod 48 on the whole thing on both sides. So 1 mod 48, still 1. All this side, my mod 48, makes this part go to 0, right? Any multiple of 48 goes to 0. And so I have 1 is equal to 11 times 35 when I'm working mod 48. And so there's my 35. The coefficient out in front of that is going to be your inverse, assuming it is within the proper range between 1 and 47. Okay, if it was like negative or something, you have to convert it. But that's going to be our answer. And so let me prove that to you. You can always check your answer. You can always check your answer. So 11 is going to be the inverse of 35 mod 48, and we just discovered that. Let's prove it to ourselves. So 11 times, let's do 11 times 35. And let's work mod 48. So that's equal to 385 mod 48 really is 1. So yeah, when you're working mod 48, you multiply 35 by 11, and then you get 1. That's what it means to be an inverse. Cool. So that's the answer, and that's how you find it. And that is as much as I want to melt your brain for the day. So we still have more to talk about. This is a longer set of slides, but we've come very far. Okay, we've learned a lot of cool things. Definitely start that homework so you can get started practicing all this stuff. But that's where I'd like to stop with the lecture today.